Almost all the planet's earthquakes and volcanic eruptions happen in one place. The Ring of Fire! No, really, that's what it's called. Dope, I know. Nearly the whole Pacific Ocean is bordered by this treacherous region. We're talking the sites of some of the biggest earthquakes ever recorded. Massive volcanoes in Indonesia, Russia, even Antarctica. Huge explosions and fractures that happened on land and underwater. But why? What makes the Ring of Fire so fiery? Hi, I'm Sage, and this is Crash Course Geology. The Ring of Fire came about thanks to a billions of years long process where all the continents, all the ocean floors, everything that makes up Earth's outermost layer shifts around, pulling apart, crashing into each other. What's that, Dwayne? Oh yeah, that does sound like one of your family reunions. Let's break down how all that works. Earth has three main layers: crust, mantle, and core. Its rigid outer shell, called the lithosphere, is made up of the crust and the uppermost part of the mantle. But the lithosphere isn't just one solid piece of Earth. It's broken up into plates, huge slabs of rock that are puzzle pieced together. They're generally composed of both continental lithosphere, which makes up the land we can see, and oceanic lithosphere, which makes up the sea floor. Continental lithosphere is made up of mostly thick, lightweight granite, while oceanic lithosphere is made of denser, heavier rocks like basalt and gabbro. Roughly 95% of Earth's surface is made up of 7 major plates, with the rest covered by much smaller ones. And underneath those plates is the asthenosphere, where intense heat from Earth's core warms up the mantle rocks so much that they flow around and bend like taffy. The hottest rock creeps upwards towards the surface, and the colder stuff at the top sinks back down, creating convection currents, or heat-based flow cycles. And those currents power important forces that move Earth's plates in one big geologic slow dance called plate tectonics. Plate tectonics shapes our world, literally. And all of the action happens where plates meet, at their edges, called plate boundaries. Like at divergent boundaries, plates move away from each other. As oceanic plates diverge, the hot mantle rock wells upward and some erupts as lava, which cools and hardens into new oceanic crust. This process is called seafloor spreading, and it's mainly generated by ridge push, the gravity-driven force that causes the new seafloor to sink downward and pushes away the older crust. When continental plates diverge, the Earth's crust thins and breaks apart, creating features called rift valleys. We can see this happening in East Africa, where the Nubian and Somalian plates started pulling apart about 25 million years ago. Meanwhile, at convergent boundaries, plates move toward each other. When a dense oceanic plate meets a more buoyant continental plate, a process called subduction happens. The denser plate slides underneath the other one, returning that rock to the mantle. This is primarily thanks to slab pull, the gravitational force that yanks plates downward. And this is largely what happens in the Ring of Fire. It's full of subduction zones. As the oceanic plates slide deep underground, they release water into the hot rocks above, which has an explosive result. That water can cause the overlying rocks to melt, driving tons of volcanic activity. And if two dense oceanic plates meet at a convergent boundary, subduction can create huge depressions in the surface, like the Ring of Fire's Mariana Trench, which contains the deepest point in the world. It's on Dwayne's bucket list. Now, when two continental plates converge, watch out, because instead of subducting, they'll smash into each other, forming massive mountain ranges, like the Alps and the Himalayas. When continental plates converge with oceanic ones, the continental plate usually wins, staying on the surface as the denser stuff is forced down. But it's not always a competition. Sometimes plates move past each other, at spots called transform boundaries. You can think of these plates like pieces of sandpaper. They don't easily slide past each other. Eventually, that stress reaches a point where the ground moves with a jolt, aka an earthquake. The San Andreas Fault in California is a transform boundary that has had many earthquakes, like the Loma Prieta earthquake in 1989, which folks in my neck of the woods still talk about. But that kind of ground rattling can happen at all types of plate boundaries when there's enough stress. Plate movements have shaped what the Earth's surface looks like throughout our planet's history. In fact, at multiple times in Earth's past, the shifting tectonic plates have caused all the continents to collide and form one giant supercontinent, the most recent one being Pangaea, around 200 to 300 million years ago. It's like seeing Earth in her awkward phase. So yeah, plate tectonics has been happening for a long time, keeping the Earth's surface in constant motion for something like 3 billion years. The continents move an average of about 1.5 centimeters a year. That means that in all of recorded human history, the ground below you has shifted probably about 76 meters. That's only about as wide as a professional soccer field. That creeping movement is way too slow to feel. So, how do we know it's actually happening? Way back in the 1910s, German geologist Alfred Wegener looked at a map of the world and noticed that the continents looked like they fit together, almost like puzzle pieces. And he built a theory to explain what he was seeing. Continental Drift. He believed that the continents were moving slowly around the Earth, together and apart, drifting through the crust like icebergs in the ocean. He's even credited with coming up with the name Pangaea, meaning all of the Earth. But the geological community dunked on Wegener pretty hard. At the time, most geologists thought that the continents formed and moved vertically, not horizontally, driven by the heating and cooling of Earth's surface way back when it formed. But Wegener was onto something, and his idea laid a foundation that other geologists built on. Let's hang out with some of my geology rock stars. For a long time, we had no clue what the seafloor looked like. Most geologists thought it was just flat. But in the 1950s and 60s, American geologist Marie Tharp and her collaborator Bruce Heezen used sonar to map it. Given the culture at the time, Bruce got to gather data aboard research ships, while Marie was forced to stay on land and make maps. 'Cause she was a lady, with pens, ink, and rulers as her tools. She and her colleague, Hester Herring, methodically plotted each data point. And what the team discovered was incredible. Not a flat, barren wasteland, but a 40,000-mile underwater mountain range that circled the globe like a seam on a baseball. The mid-ocean ridge turned out to be a series of divergent plate boundaries, where the mantle wells up as plates pull apart, forming huge mountains and driving volcanic eruptions. This was a major point in favor of plate tectonics theory. Over the course of several years, Tharp and Heezen worked with Austrian artist Heinrich Baron to paint an accurate map of the entire seafloor. And in 1977, the World Ocean Floor Panorama was published. 20 years later, Tharp was named one of the 4 greatest cartographers of the 20th century by the Library of Congress. In 1999, Tharp said that at the start, "I had a blank canvas to fill with extraordinary possibilities." And she did just that. It took decades and many lines of evidence for the theory of plate tectonics to develop and gain consensus. But the combined efforts of geologists across the world brought us to the conclusion that the Earth really does move underneath our feet. And that consensus didn't look like a bunch of geologists saying, sounds about right. Science historian Naomi Oreskes called it the first theory to ever be accepted in the entire history of Earth science. Can you imagine that level of harmony? It'd be like if every film critic agreed on the best movie ever made. Dwayne's favorite? Shrek 2. Today, we know that plate tectonics shaped the planet we know and love. It's why Europe is warm enough for people to live there, while Antarctica is uninhabitable. Unless you count the penguins. Regardless, knowing about plate tectonics helps us prepare our communities for disasters like volcanic eruptions, earthquakes, and tsunamis. And it gives us a window into Earth's past. Earth's plates are still moving, right now, and we're still learning more about them. Like, we don't know exactly what our planet will look like in the distant future. Some predict that 250 million years from now, Earth may be home to another supercontinent, similar to good old Pangaea. And we don't know how long plate tectonics will last. One day, when the Earth gets old enough to cool way down inside, plate tectonics will come to a stop, reshaping the world in a big way, one last time. That could look like mountains eroding into plateaus, Earth's magnetic field stripping away, and continents sinking into the ocean. But that's potentially billions of years away. Plate tectonics isn't going anywhere anytime soon, and neither is our massive, magnificent planet. Our planet moves us. And not just in the tear-jerking, wow, Earth really is something kind of way. The land beneath us is constantly shifting, creating something new every day, albeit very slowly. Go at your own pace, girl. As long as the seafloor keeps spreading and gravity keeps pulling, Earth's plates will be carrying us around, shaping and reshaping the world as we know it. Next time, we'll talk about how plate tectonics builds mountains. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed at our studio in Indianapolis, Indiana. It was made with the help of all these spectacular people. If you want to help keep Crash Course free for everyone, forever, you can join our community on Patreon.